Hi folks, in this video, I'm going to introduce our machine learning work that aim to model structure flow heat interaction in rough channels. Rough channel exist in nature and also in many engineering systems. So the surfaces of most nature systems are rough. So as you can see in this picture, there are many rocks in rivers, in sea and lakes, and most of the flow systems include very rough surfaces. And many engineering systems, such as tubing or piping systems, we intentionally make grooves or some surface roughness to generate flow circulation and complex flow patterns. And the reason for making rough channels in engineering systems is to enhance the heat transfer performance. So Nusselt number represents the heat transfer performance, and by incorporating the surface roughness such as rectangular, triangular, or something like this, you could improve the heat transfer performance from this baseline um, solid line to these scattered the symbols representing the performance of rough systems. So understanding the fluid dynamics and the properties of the rough channels seem to be very important when you design such system and when you're trying to understand the basic physics. So as you can see, there can be many different rough surfaces. Like, so for example, here I show roughness channel 1 having roughness something like this. And here I show roughness shape 2, which is quite different from the first one, right? And depending on the gap and height of the roughness, you can generate flow circulation at a certain location, and the boundary layer on the surface will separate at a certain location. However, of course, as you can expect, mathematically, it is really extremely challenging, or maybe it's impossible to derive a simple formula to express the convection coefficient along the channel for many different rough channels. So here I show the square symbols corresponding to the distribution of convection coefficient in roughness shape 1, which is this. And these red circles correspond to the distribution of H value convection coefficient within this roughness shape 2. As you can see, they're quite different. And just imagine that you have like 100 different roughness shapes, and they will exhibit very different behaviors. So you will realize that there's no simple mathematical form that can express all those roughness channels. So the goal of this work was to develop a machine learning technique that can mathematically express the convection coefficient distribution for many different scenarios. And in this work, we succeeded to express 243 different rough channels using a single machine learning model. And to do this job, we employed random forest technique, which is very popular machine learning technique. So this is different from artificial neural network, and we will go through the basic principle in the next video. But briefly speaking, in the random forest, you will take a feature vector or input vector, and this vector basically describe the geometry of your rough channel. So the vector consists of the height of the roughness features. So for example, if your rough channel includes 5 bumps, something like this, you can define the height as E1 to E5, or if your channel has like N bumps, you can measure those heights as E1 to En, right? So you can describe the channel surface geometry using this vector. And if you put this vector in your random forest model or decision tree model, your model will direct your input vector to a certain branch. And there's um, um, many different branches uh, which are arranged in series. So going through multiple branches, your input vector will be located at a final node, and the final node actually has the description of the convection coefficients in a certain rough channel. So the final output corresponds to a vector consisting of convection coefficient from H1 to Hn. So basically H1 corresponds to the convection coefficient around this location, E1 location, and Hn corresponds to the convection coefficient value at En location. So if you put in like different channel geometry or different feature vector, you will end up with different final node, and you will take the different description of convection coefficient value. So by doing this way, you can make a single machine learning model that can be used to describe the distribution of convection coefficient for a large number of different rough channels. And briefly speaking, there are many different things to optimize to construct a good working random forest model. So, um, so as I explained in the previous slide, your input factor should go through multiple nodes and multiple branches. So the question should be how many nodes, how many branches should exist within the tree is a problem. And in the random forest model, random forest algorithm, you need to build multiple decision trees. So basically, you will not have a single tree to make a final decision, but instead you will have multiple trees that predicts different output values by different trees. But at the end, you need to take an average of all the trees to get the final decision. So each machine learning model, each decision tree uh, will not give you exactly correct answer. There's a probability that each tree gives different values depending on how they're trained and how they are structured. So to be accurate, to be safe in machine learning technique, we can build multiple machine learning models, and we can let them actually take an average to generate more reliable final answer. So how many trees should be included in your random forest is one of the important parameters. And then for the random forest model generation, you need to have some training data. So your model should make some dummy prediction, and then those answers should be compared with the true answer, such that your model is accurately optimized or structured. So in random forest model, as I said, the input vector should be accurately directed um, over multiple branches. So your random forest model will be trained to accurately direct the input vector over multiple branches. So that's the purpose of the training. And as you can see from this plot, so basically we are comparing the random forest prediction along the x-axis versus the convection coefficient values predicted from conventional numerical simulation model. So as you can see, they compare well after a successful training. So if your training is successful, the random forest model prediction should be similar to the traditional simulation methodologies. And once the model is well trained, now you can apply your model for um, many different scenarios, which uh, which which is not necessarily the training scenario. So in this model, we use the trained random forest model to predict a new scenario. So those are indicated by these red dots. And then we compared um, these result with a numerical simulation model. And as you can see, the random forest model gives highly accurate result compared to the simulation. But of course, testing your random forest model to a new scenario has some limitation. If the rough channel looks so much different from your training scenarios, your random forest model will give very inaccurate result. But if you test your random forest model for reasonably close scenario to your training scenarios, then your model prediction will be still accurate. So that's actually the basic introduction of the random forest prediction for rough channels. And this work um, has been published in this research article, and the title is Machine Learning for Heat Transfer Correlations, and the journal is International Communications in Heat and Mass Transfer. So in the next video, we will go through the principle of random forest model, and uh, in the following video, we will see more details of this research article. Okay, so thank you for watching this video.